Hey everybody, welcome to part 2 of my AP Calculus Unit 5 review. Let's just get straight into it with more analytical applications of differentiation. We're going to start with some sketching, some pretty easy stuff. Really not too hard once you actually think about it. So let's just start here. So in this first example, we're given f of x, right? Just some function, and they want us to sketch the derivative of this function on this like graph, I guess, basically. So this really isn't too hard. The derivative is just going to be all of the slopes of these pieces, right? So let's just calculate. So these are straight line segments, so that should be pretty easy. So let's calculate the slopes for each of them. So here we go up 2 over 1. So our slope across this entire line segment here is going to be 2. Positive 2, right? So we'll just do this and that. And notice how I'm using open circles because basically the same reason you cannot be differentiable at an endpoint. Basically I talked about that pretty extensively last time. But yeah, so I'm just going to draw a straight line through there. And again, it's going to be a straight line because I'm at a constant slope during that time. So I hope that makes sense there. Okay, so then over here we're going down 3 over 1. So it's going to be a slope of negative 3. So I'm going to go down here between this interval and a slope of negative 3, right? Okay, so then over here between negative 2 and 0, we have a slope of 0, right? So it's not going anywhere. So let me just put that here. So here and here we have a slope of 0. All right. So again, really not too difficult. And then here between 0 and 1 we have a slope of 1. So let me just put that here. 0 and 1 we have a slope of 1. And then again we have a slope of 0 between 1 and 2. So let me just put that back down here. All right. Okay, and then our function doesn't actually exist between 2 and 3. So if our function doesn't exist, then our derivative cannot exist. So I can't put anything between 2 and 3, right? Because we don't have anything to differentiate. So yeah, let's just move on. We have one more segment here between 3 and 4. Our slope appears to be negative 1. So we just go between 3 and 4, and our slope is negative 1. So I hope this makes sense, the whole process I did. Basically, you just take the slopes of each of the line segments. If you have straight line segments, it's pretty easy. Just calculate the slopes, and you should be able to quickly do this. And you should you should be able to go from here to here. If you know that the slopes of each of the line segments, you can construct something like this. Now, it might look exactly like this, but it could look a little different. This could be shifted up or down a little. Like maybe this line segment is instead like down here. This whole thing could be shifted up. Each of the pieces could actually be shifted to a different position. Now, why is that? Well, that's because your slope doesn't depend at all on your position. Just like if all the information you had on this line segment was that your slope was positive 2, that doesn't determine where it goes. Your slope can be positive 2 here, it can be positive 2 down here, wherever you want it to go. So that's kind of the freedom if you're going from an f prime graph to an f graph, and that's what we're going to be doing down here, and I'll show you about that in a second. But yeah, let's just do another one of these examples from a g of x graph to another derivative of g graph. So here, we're not given straight line segments, and I didn't even label the y-axes because they're really not important. Basically, we just have a very simple function, and we're trying to find its derivative. Now, we really don't know a lot of information. We don't know the exact derivatives at each point. We can compare the slopes at particular points, but that's going to be too time-consuming for us. Really, all we need to know is where is our slope, positive, negative, 0, just where is that? So let's start. First, let's identify where our slope is 0. That occurs here, and also down across this entire interval. So if our slope is 0 there, we can basically just put our slope to be 0 here. Okay, and it's also going to be 0 across this entire interval. And I'm going to say it includes, actually no I can't, yeah no I cannot. So let me just say it's 0 here, 0 here, and then across that entire interval. Okay, so now what's happening between these segments? So between -2 and -1, our slope is positive. So again, remember, if our derivative is positive, then our derivative here, I'm sorry, if our slope is positive, yeah, if our derivative is positive, so that means our slope is positive, it's increasing. That means our derivative is positive, and really they mean the same thing. Basically, if you're increasing, if your function is increasing, that means your slope is positive, so your derivative is positive. And what that means here is that it's going to be somewhere up here in the positive region of your graph. So it doesn't matter where, because again, it doesn't really matter. But basically, I'm just going to say, well, we don't know anything about here, we just know, we don't know. So I'm just going to put it here. And again, so our slope is positive, so it can do whatever it wants on this region. Oh, it has to actually be differentiable, of course, so I can't make the slope like infinite. Hold on. I'm trying to show that you can kind of do whatever you want with it, but I'll just be simple, I guess. Yeah, so it really doesn't matter what it looks like, as long as it's positive over the entire region. And then between -1 and 0, it's going to be negative, right? And then here we already put that it's 0, and then on this interval, it's again negative, so I'm just going to move it down again. And that's it. That's just our sketch. And again, you can make it as creative as you want, but really you just want to focus on actually doing it properly, you know? Okay, for the last example, we're going from the derivative to the original function for h of x. And as I said, your position doesn't really matter, so you can start wherever you want. Okay, so let's think about this. So here, this is telling us that our derivative is positive. So over this entire region here and here, our slope is going to be increasing. Or I'm sorry, our function is going to be increasing. Our slope is positive, so our function is increasing. So we know that our slope is increasing. So let me I can put it wherever I want. I'm going to say we're going to start here. Actually, I think I should have put, I should have put open circles here. Yeah. Alright, so yeah, basically our function is increasing between -2 and -1. So let me just do that. Okay, and then it's equal to 0, so the derivative is equal to 0, so the slope is 0. So let me just make sure that the slope is 0. There we go. And then it's negative for this portion, so it's negative. So it's negative for a little bit. Yeah, that's kind of weird. I guess I should have been a little better with that. But yeah, it's negative for a little bit, and then it goes back to being 0, and then it's positive. Our slope is positive. Yeah, so hold on. Oh, and I'm sorry, I was getting confused. No. So, yeah, it's really easy to get confused here, because this is the slope, and you're trying to put it in this. So, over here, your slope is going to be negative. If this is negative, that means your slope across this is going to be negative. So this is going to be negative across here. And then it's going to actually be positive again once you enter this. So it's going to be positive actually the whole rest of the time. except here at this particular point, and I'll show you what I mean. So we're gonna have an open circle there, and then it's just gonna be positive, however you want, whatever. So this open circle, it just means that your derivative doesn't exist. So there could be a couple ways your derivative doesn't exist, but the best way to do it is to do like a cusp. Oh wait, yeah, no, we can't do a cusp because, yeah, wait, what am I doing? Oh yeah, so since we can't do a cusp, because if we did a cusp, it would have to be like that, and then you can see that your slope is negative for a little bit there. So the thing you can do is just make it not continuous. So again, that could just be having an open circle there, or having like a horizontal asymptote, or I'm sorry, a vertical asymptote. So if we had like a vertical asymptote, then it could look something like this. Oops, it cannot touch the vertical asymptote. Like that, something like that. So it's increasing here, increasing there. I don't know. I don't really think they'll ask you something like that where you have to like think of, but like if you know like some of the resources you have, then that's good. So these are sketching some graphs. I hope this kind of makes sense to you, how you can just calculate some of this line segments, the slopes of them, or you can really just look at it, and you should definitely be able to go back and forth. This is definitely a lot harder than this, because here it's like, oh yeah, just find the slope, and then here it's like, the slope, it gives you information about the slope, and you have to convert that into a line, so it's kind of hard, but it is what it is. Alright, so let's move on to the final topic of this video. Alright, so here we have an optimization problem. So I hope you guys have already gone over that. But basically, I'm just going to give you guys a quick example. So, rectangular plot of land. So let me just draw a rectangle here. Just a brief, oops, let me actually make it a good rectangle. There we go. So it is enclosed by a fence, and it's divided in half by another fence. So let me just divide this in half. All right. We have 100 feet of total fencing. We want to maximize the area. So first, what is our area going to be? So if we call this entire thing X and this entire thing Y, so then our area is just going to be X times Y. And our perimeter, so because we need the perimeter because it's we're given the amount of fencing actually used, our perimeter is equal to 2x plus 3y, because there are 3 of these guys, so 2x plus 3y, so that's something you got to be careful about. And we want to try to turn one of our y's into x's or x into y's. We can really choose, it doesn't really matter. So I want to solve for this in terms of like y, so we can say that y equals a over x, right? Just, you know, it doesn't really matter. So then we can say that perimeter is just going to be 2x, oops, I don't know why it bolds sometimes, plus 3 times, wait, what am I doing here? Oh, I'm sorry, I did it the wrong way around. Basically, we're trying to solve for area, so we want to try to find that, hold on. Okay, so basically, we need to try to find our perimeter. We want to solve something in terms, so actually we know that this is 100, right? Because that's given to us. And so we can say that, I don't know, 2x is equal to 100 minus 3y. So we can say that x is equal to 50 minus 3 halves y. Right? Okay, so then we can plug that into our area equation, because that's obviously what we're trying to find. So we can say that area is equal to x times 50 minus 3 halves. Oh, yeah, this is going to be y times 50 minus 3 halves y. Yeah, there we go. So basically we're just substituting and then multiplying. Yeah, substituting basically. So this is equal to just, we can just distribute this as 50y minus 3 halves y squared. Okay, so let me just do our area prime equation. So this is just going to be 50 minus, and then the derivative of this is just going to be 3y. So 50 minus 3y, set this equal to 0, because we're trying to find a local maximum, actually an absolute maximum. So we can say that 50 equals 3y, and then y equals 50 over 3. And, okay, so I made a small mistake, but basically all you gotta do, so 50 divided by 3, that's just about 16.667, and then you plug that back into, you basically just plug that into here, 50 minus 3 halves times 16.667, you'll get 12.5, and then you just multiply these two together to find your area, because the area is just x times y, and you get 416.667 feet squared. That is the maximum area you can have. You can have less area than that, but this is the maximum possible area you can have with that amount of fencing. So yeah, thank you guys for watching. Sorry I'll always have to split these into two. It kind of sucks for me, and I'm sure it's kind of annoying for some of the viewers, especially if you're not really here for this kind of content. But I hope it helps you regardless. So thanks for watching, and I will see you in the next video. Bye guys.